Good evening, dear students.
Evening, sir.
Good evening, sir.
Yes, we shall start off the class. Still, there are many students yet to join. But anyhow, we shall start working out numericals. We have completed the Kohlrausch and two problems on that. Okay. Uh, Based on Kohlrausch we'll take a few more problems and then move on to Faraday's. Okay. So, two questions are taken. We'll take up the third problem. Come on. Write down. Ayo, could you please be loud? 1 second, I'll just see what has happened here. Okay. Can you all hear me now?
Yes, sir.
Yes.
Okay. I think Prajwal,
Sir?
ಅದು ಇನ್ವೈಟ್ ಐ ಥಿಂಕ್ ಇದಕ್ಕೆ ಸ್ಟಡಿ ಸರ್ಕಲ್ ಹಾಕ್ಬಿಡಿ. I forgot that. ಕೇಳಿಸ್ತಾ ಪ್ರಜ್ವಲ್?
Saturday, sir.
Okay. Okay. Students, we'll take up this problem. Write down. So can you all, I think audibility, is it better now? Can you all hear me?
Yes, sir.
Yes, sir.
If the molar conductivities at infinite dilution at 293 Kelvin for HCl, sodium acetate, and sodium chloride are 383, that is 383.5, 78.4 and 102.0 Simon centimeter square respective. Calculate the limiting molar conductivity of acetic acid at the given temperature and dilution. The given temperature and dilution. If molar conductance at some other dilution at some other dilution. That means other than infinite dilution. Okay, other dilution is hundred Simon centimeter square at 293 Kelvin. Calculate degree of ionization. Degree of dissociation. So you need to calculate limiting molar conductance of acetic acid from the data and also alpha.
Sir, limiting molar content
Huh.
359.9.
Alpha.
1 minute. Sir, is alpha 0.27. 0.278, sir.
0.278. Correct. Good. So if you want lambda naught of acetic acid, sodium acetate plus HCl minus lambda naught of NaC. So HCl is 383.5 and sodium acetate is 78.4. Okay. Then they're asking alpha. They have given some other concentration, lambda m at some concentration C, 100.0 Simon centimeters. Therefore, alpha is equal to lambda m divided by lambda m naught. Right? See here. Okay. 359.9. 0.278. That's all. Let me know if it is complete.
Yes, sir.
Okay. Okay. We'll take up one more problem. Conductivity of 0.0024 molar acetic acid is 7.896 into 10 raised to minus 5 centimeter. Lambda m infinity of acetic acid is Simon centimeter square per mole. Calculate molar conductance acetic acid and also find the dissociation constant. Conductivity K has been given. Concentration is given. Lambda m infinity is given. So we need to find lambda m, correct? And then you need to find out K, dissociation constant. So concentration
2.76.
How much? Which is that?
Molar conductivity.
How much?
32.76.
Okay. Molar. Kappa. Centimeter. By using these two, first you need to calculate lambda m. Then they have given lambda m infinity 390.5. By using lambda m infinity alpha question mark, then by using alpha K question mark, dissociation constant Ka for acid A. Come on. What is Ka? What is dissociation constant?
Sir, 1.86 into 10 to the power minus 5.
Correct. So it is in centimeter. K by C into 10 raised to 3. Divided by 0.0024 into 10 raised to 3. This can be 2.4 in 10 raised to minus 3. Go to numerator plus 3. 10 raised to 6. 10 raised to minus 5 means 10. 78.96 divided by 2.4.
32.76 Simon centimeters.
32.76, huh?
Yes, sir.
Step 2, need to go for alpha and then K. We have calculated 32.76. They have given lambda m infinity 390 point. Alpha 0.0.
32.90.
32.76 only.
32.76 is correct. Madam, you can calculate again.
Okay, sir.
0.084.
0.084.
0.084. Okay, then Ka. What is the expression for Ka? Asphalt dilution. C alpha squared divided by 1 minus alpha. 0.0024, right? Into 1 minus 0.916.
(1.86 into 10 power minus 5).
1.8.
86
10 raised to
minus 5.
right. So those who are writing can copy down. Let me know when it is complete. Let me know if it is complete.
Done, sir.
Yes.
Done, sir.
Right. So these are some of the numericals on Kohlrausch law. So we shall take up next concept, that is Faraday's laws of electrolysis. Okay. One. Okay. One second. Yeah. We'll take up now Faraday's laws of electrolysis. Faraday's laws of electrolysis. Now, when you pass electric current through any electrolyte solutions, then you are going to induce some chemical reactions. Preferably, some reactions particularly take place at anode, and some reactions take place at cathode. So always during electrolysis, anodic Fill in the blank.
Oxidation.
And cathodic
Reduction.
reduction, always. So that is how exact. During electrolysis, there are certain laws to be followed. That is what it is formulated by Faraday. Faraday tried to conduct electric current through solution way back in 19th century beginning itself. John Dalton gave atom, and he told atom is the final entity. And then Faraday started after some 25-30 years, around 1830 itself. So then he started conducting electric current through solution and gaseous phase, all those. There only people started getting, oh, atom cannot be final, and there should be some subatomic particles. That led to electron, proton, neutron discovery things. Okay. Now, what are these Faraday's law? There are two laws. Those two laws, you know, first law and second law. See, you know this. Okay. What is first law is what we need to state. Now we'll take up first law. See, I will not state, I'll just explain, but you only have to state this. Okay. Faraday's first law. Okay. They may ask you, Yen law, first law. So listen to me. I'll just explain what it is all about. And you have to make a statement for this. What is this blue color solution?
Electrolyte.
Which electrolyte is this question?
Copper sulfate.
Copper sulfate. Copper sulfate solution. Okay. We are going to introduce what? Electrodes. These are conventional electrodes. They are not electrodes, single electrodes. In case of single electrodes, the charge becomes opposite. Whereas in case of these electrodes in electrolytic cell, that is voltaic cell, where chemical energy converts to electrical energy. This is electrolytic cell, where electrical energy converts to chemical energy. So I'll write sign. You should tell me what it is. Positive electrode is
Anode.
See, thoroughly thought and then give the answer. Otherwise, it will get confused. So positive attracts negative, anion, anode. Okay, negative attracts cation, cathode. Whereas in case of voltaic cell, it is quite reverse. Correct? No. In both the electrolytic cell and voltaic cell, one thing is common. I'll give you sometime later under the differences between electrolytic cell and voltaic cell. Okay. The sign for anode and cathode in electrolytic cell and in voltaic cell is different. Here, positive anode, negative cathode. Their negative anode, zinc rod, for example, Daniel's, and positive is a cathode there. But in both the cells, one thing is common. Can you tell me what is that one thing common? That mantra, 4 o'clock mantra.
Anodic oxidation, cathodic reduction.
Where is our Kishan Balaji? So you have asked me time and everything, you are not repeating. So anode and cathode, the electrode reaction would always be same, anodic oxidation and cathodic reduction. So that is the thing. Okay. Now I'm going to pass electric current. Where do you think copper gets displaced?
Cathode. Cathode.
Copper gets displaced or discharged or deposited or liberated, whatever you can say. Okay. So upon passing electric current, copper gets deposited at the cathode. By passing some amount of current, some quantity of copper deposits. I'll pass little more current. How much copper? Little more.
More.
No. I am going to pass little more current. Hello?
Till 1.8 increases.
How much it increases?
Till some certain volt.
Beyond that?
It remains constant.
Why? What is this? You're telling something new. Why it becomes constant beyond certain point?
I can't explain.
Copper ions are exhausted.
The copper will become empty.
Oh, that means you have gone up to that stage. Okay, where till copper gets exhausted. Okay, that may be right. When it gets exhausted, nothing to discharge. Something else will happen in the solution. Okay, before that point itself. Okay, Kishan sir. Before that point, I'm keep on passing the electric current. Copper keeps on depositing. Little current, little copper. More current, more copper. And what you have understood is first law. That's all. Now, can you tell me what is the statement of first law? That itself is first law. What is first law? Can you make a statement for this? Anybody?
Deposition of copper is directly proportional to the current.
Oh, that's fantastic, I said. So I expected somebody to say little copper, little current, little more copper like that. Anyhow, that cannot be a statement. Right. Exactly. During electrolysis, the amount of the substance deposited at the cathode or displaced at an electrode. Why only cathode? Even at anode, some anions will be oxidized. So during electrolysis, the amount of the substance in general need not be only metal. Amount of the substance displaced or discharged at an electrode is directly proportional to the quantity of electric current that is passed through the solution. Is it okay? During electrolysis, the amount of the substance displaced at an electrode is directly proportional to the quantity of electric current that is passed through the solution. Is that okay? So let's make a statement. Okay. So first law. The statement is during electrolysis, the amount of the substance, displaced at an electrode is directly proportional to the quantity electric current proportional to the quantity of electric current passed through it. The electrode is directly proportional to the quantity of electric current passed through it. That's it. So this is first law. Let us give a mathematical form for this. Okay, mathematical. The amount of the metal displaced is W. It is directly proportional to the quantity of electric current Q. Basically, W proportional to Q. Or if you want to make an equation of it, then it's equal to a constant Z into Q. Z into Q. Also, or you can say, but quantity of electric current Q can be calculated as product of current strength in amperes, time in seconds. Therefore, finally, we can write W is equal to Z into IT. So the question that we need to answer is, what is Z? Where? Let me write other terms also. I, current strength, in amperes, T, time in seconds, W, mass of the metal displaced, all those things fine. And here Z is electrochemical equivalence. Electrochemical equivalence, it is abbreviated as ECE, electrochemical equivalence of the metal displaced at the electrode. Okay, electrochemical equivalence of the substance displaced. Now, if you want to know what is Z, it is what is ECE for a given substance which is displaced. Okay, so in this equation, if you want to find the meaning of Z, the terms which are associated with Z, I and T, should be made as 1. What do you mean by that? When I is equal to 1 ampere and time T is equal to 1 second, okay, then W is equal to Z. What does it mean? Electrochemical equivalence is simply nothing but amount of the substance or metal, whichever, in case of copper sulfate, copper. So electrochemical equivalence of copper is nothing but the amount of the metal copper displaced at an electrode, that is cathode, by passing 1 ampere current for 1 second. Just 1 second. Correct now? I into T is Q. This equation, right? I into Q. So I into T. So 1 into 1, 1 coulomb. So if you pass 1 ampere current for 1 second, it is like passing 1 coulomb of charge. So you can also define Z as electrochemical equivalence is the amount of the metal displaced at an electrode by passing 1 coulomb of charge through its solution. So if you want to find out, say, electrochemical equivalence of copper, pass 1 coulomb of charge or 1 ampere current for 1 second. Then how much of a copper is deposited at cathode? That is what is electrochemical equivalence of copper. That's all. Come on, make a statement for this. Come on. It's the amount of metal displaced at an electrode by passing 1 ampere current for 1 second. Nothing but 1 coulomb of charge. Correct? That is what is that. Fine. If you want to find out unit of Z, what could be unit of Z? Anybody? Z is nothing but W by Q. So gram per coulomb. Quantity is coulomb. If it is done, I'll proceed.
Wait, sir.
Pardon me?
Wait, sir.
Okay.
Sir, could you scroll down a bit, sir?
Puneet, once again.
Could you scroll down a bit, sir?
Okay. Little more. That's all.
Thank you, sir.
And W is amount of the substance discharged. Is it complete?
Yes.
Done, sir.
Now let us give an expression for Z. Let's see how to calculate Z by using a formula. Z is the amount of the metal displaced at an electrode by passing 1 coulomb of charge. Okay. Now, before we could give an expression for Z, we need to know something called as Faraday's constant. Did we come across Faraday's constant before?
965000.
Advanced equation.
Exactly. Faraday's constant. Okay, it is capital F. What is basically Faraday's constant? You know, it is the charge on one mole of electron. It is the charge on 1 mole of electrons. That is what is 1 Faraday. So charge on 1 electron into Avogadro number would give this. So therefore, 1 Faraday is found to be 96,487. 96,487. What is the significance of this quantity of current? Let's see. Now, let's say I have a silver nitrate solution through which I'm going to pass electric current. My intention is to deposit silver from the silver nitrate solution. Okay, in the electrolysis of silver nitrate. I want to deposit Ag ions. So if I want to deposit Ag plus into Ag, I need to give electron. I need to reduce. So tell me, if I have to deposit 1 mole of silver, how many moles of electrons must be added? How many moles of electrons are required to
1 mole.
1 mole of silver? 1 mole. 1 mole. Okay. I want to, through copper sulfate solution, I want to pass electric current and deposit copper. But what is the charge on copper? Cu2 plus.
Yes.
I want to deposit 1 mole of copper. So tell me, how many moles of electrons are required? 2 moles of electrons I need to add. Similarly, there is aluminum chloride solution. Okay, I want to deposit aluminum. Aluminum is there as Al3 plus ion. And if I want to precipitate Al3 plus to Al, I need to give how many moles of electron? 3 moles. Okay. So 1 mole of silver requires 1 mole of electron. 1 mole of copper to deposit require 2 moles of electron. 1 mole of aluminum to deposit require 3 moles of electron. Right? So what is charge on 1 mole of electron? What is charge on 1 mole of electron? We have done some time back, no? Some 10 class before.
1 farad.
Just now we have done. I say, why are you so silent? Charge on 1 mole of electron is 1 Faraday. So can I speak in terms of Faraday now? I want to deposit 1 mole of silver. How many Faraday required?
1 Farad.
So 96,487 quantity of current you need to pass through silver nitrate, and you will get 1 mole of silver. That is 1 atomic mass, which is 108 grams. Okay, so 1 Faraday. I want to deposit 1 mole of copper. How many Faraday?
2 Farad.
2 Faraday.
How many Faraday? In case of aluminum, 3 Farad. So then, for 1 mole of copper and aluminum, the quantity of electric current required is more than 1 Faraday, 2 Faraday, 3 Faraday. Then, how much is deposited by 1 Faraday? So then you can use this equation, the equation which we have used some time back. The equation is equivalent mass of an element is equal to its atomic mass by what? Equivalent mass is equal to atomic mass by what?
Valency.
Valency. Correct, no? So tell me, what is equivalent mass of silver, Ag plus? Its atomic mass by valency 1. So what does it mean? Equivalent mass and atomic mass both are same for silver. Correct, no? So 1 equivalent mass is equal to 1 atomic mass. It is deposited by how much of how many Faraday? 1 Farad. So 1 Faraday, 1 atomic mass of silver, nothing but 1 equivalent mass. Tell me, what is 1 equivalent mass of this is copper. What is 1
Atomic
equivalent
mass by 2.
Atomic mass divided by 2. Okay, so 1 atomic mass is deposited by how many Faraday? You can see here 1 atomic mass of copper is deposited by 2 Faraday. So 1 equivalent mass is deposited by 1 Faraday. Can I? Similarly, what is equivalent mass of aluminum? Atomic mass divided by charge, valency 3. 1 atomic mass is deposited by how many Faraday? 3 Faraday by 3. So 1 equivalent mass is deposited by 1 Faraday. What does it mean? So there is some clarity now. If you pass 1 Faraday of electric current, that is 96,487 coulomb of charge through any electrolyte solution, how much of the metal gets displaced, or how much of the substance gets displaced?
1 mole.
1 equivalent mass, not 1 mole. 1 mole is 1 atomic mass. 1 equivalent. So, see, in case of silver, 1 mole is 1 atomic mass, 1 equivalent mass, both are same. But in copper, it is not so, no? 1 mole is 1 atomic mass, which is equal to 2 equivalent mass. I think you didn't understand. Did you understand or not?
Understood.
So, tell me, if I pass 1 Faraday, that is 96,487 coulomb of charge through any electrolyte solution, how much of the substance gets displaced? 1 Faraday displaces how much?
1 equivalent.
1 equivalent mass of the substance. Like 1 equivalent mass of silver, 1 Faraday. 1 equivalent mass of copper, 1 Faraday. 1 equivalent mass of aluminum, 1 Faraday. But here what we have written 2 Faraday. That is for 1 mole of copper. 1 mole of copper is 1 atomic mass. 1 atomic mass is equal to, for copper, it is 2 times equivalent mass. So if 2 equivalent mass are liberated by 2 Faraday, 1 equivalent mass is liberated by 1 Faraday. So what is the important significance of this Faraday constant? By passing 1 Faraday of current through any electrolyte solution, 1 equivalent mass of the substance can be discharged, displaced, liberated. Is that okay? That is the important significance of this Faraday's constant. Okay, so therefore 1 Faraday of electric current when passed through one Faraday of electric current when passed through any electrolyte solution one equivalent mass of the substance gets displaced or discharged. Gets discharged. That is important. So this data is very important for us. Okay, 1 Faraday of electric current when passed through any electrolyte solution, 1 equivalent mass of the substance gets discharged. Okay. Therefore, can we give an expression for electrochemical equivalence Z using this? What is basically Z? Z is the mass of the metal displaced by passing 1 coulomb of charge. Right? If 96,487, that is 1 Faraday, can liberate 1 equivalent mass, 1 coulomb can liberate how much mass? Can give Z. That's all. Right now? So expression for Z. So Z is nothing but mass of the metal displaced at an electrode by passing 1 coulomb of charge. So, but we know that 1 Faraday, when passed through any electrolyte solution, 1 equivalent mass of the substance gets displaced. 1 Farad. Therefore, 1 coulomb can displace how much is the question. How much? 1 coulomb can displace how much? So it is nothing but 1 Faraday can liberate 1 equivalent mass. So 1 coulomb how much? That's all. No. How much ever mass is displaced by 1 coulomb is nothing but electrochemical equivalence. Is that okay? So therefore, how do we give an expression for Z? Therefore, Z is equal to E divided by F, or E divided by F is 96,487. Now, shall we incorporate this Z expression into first law? What is first law? W is equal to Z into IT. Therefore, Faraday's first law becomes okay. So W is equal to Z into IT. In the place of Z we can write E divided by 96,487 into IT. Would you like to write down this? If so, you can write and let me know when it is complete. Or should I scroll down a little bit, Puneet?
Yes, sir.
Yeah, from Faraday's constant.
Done, sir. Done, sir.
I'll ask you simple questions based on this Faraday's constant. You just need to answer. We shall proceed. Now we know that 1 Faraday, that is 96,487, when passed through any electrolyte solution, it can liberate, displace, discharge, deposit 1 equivalent mass of the substance. Okay. I'm going to pass 1 Faraday through copper sulfate solution. Okay. If equivalent mass of copper is 32, how much of copper gets deposited?
One equivalent.
How much? What is the mass?
32 grams.
16 gram.
10 grams.
That is equivalent mass only, man. I have given not atomic mass, equivalent mass only I have given.
Oh, okay.
Atomic mass is 64, close to. Actually, it is 63. Approximately I have given. Okay. 63 means it becomes 31.5. Actually, 63.5 this. Okay. 60, so 31.75, which is approximately 30. So 32 gram of copper gets deposited. Okay. Next, I'll do this. I want to pass 0.5 Faraday through aluminum chloride solution. This time I'll not give equivalent mass. Be careful. I'll just give atomic mass of aluminum is 27. Some people say aluminum. So on. Come on.
4.5.
4.5 grams, sir.
Sure?
Yes.
Okay. Why? What is equivalent mass?
Equivalent mass is 9 grams, sir.
Al3 plus is 27 by 3. By 3 is 9 gram. So 9 gram is 1 Faraday. 0.5 Faraday, half of equivalent mass 4.5. Of what? Of aluminum. Okay. So that's fine. I'm going to pass 0.1 Faraday of electric current through HCl. Okay. 0.1 Faraday of electric current through HCl. Atomic mass. Hydrogen 1 gram. Come on.
Point 1.
0.1 what? 0.1
Gram.
gram. So 0.1 gram of hydrogen. Because equivalent mass and atomic mass both are same for hydrogen, it is 1. Because equivalent mass of H plus 1 by 1 is 1 gram. No problem. Now the question is, hmm, 9,648.7 coulomb of electric current is passed through copper sulfate solution. How much of copper?
3.2.
Sure?
Yes, sir.
Copper. Okay, because it is nothing but 0.1 farad. Correct, no? Okay. Next. Dilute HNO. So 0.5 Faraday of electric current is passed through dilute HNO3. What volume of H2 at STP? Come on.
11.2 liters.
5.6 liter.
Is it 5.6 liter, 11.2 liter, 22.4 liter, 20,400 cm3, 11,200 cm3, 5,600 cm3. Which is correct?
5.6.
Sure.
Yes, sir.
And Shu, in the chat box, what is your answer? Neeti Gandhi, Sandra. Nikita is not there today.
Yes, sir. 5.6. 11.
Sir,
Yes, sir.
Krishna Chitnis, sir.
Chitta.
Krishna Chitnis.
Yes, sir.
CHA is not there. CHI. Krishna and Kishan. How many I say? Huh? Right. So Krishna, Kishan both say 5.6. Both are of one form. Gopala. What about remaining? Sandra? Vallabh, where are you, man?
5.6, sir.
Sandra, what is your answer?
5.6.
Vallabh?
I agree with both of them. 5.6.
Is it, man? Then I'll agree with all of you.
Sir?
Huh? Okay.
5.6 only, sir.
That's correct. So, no problem. It is, equivalent mass of hydrogen, 1 gram. 2 gram is molecular mass, 22.4. 1 gram is 11.2 liter. So, but 1 gram is 1 Faraday. But how much they are passing? 0.5 gram. 0.5 Faraday will be liberating 0.5 gram of H2. 1 gram is 11.2. 0.5 gram, 5.6 liter. That is. Okay, yeah. So this is about Faraday's first law and final form. While calculating, sometimes in the numericals they'll ask you to calculate current strength, time, even equivalent mass and mass deposited. Okay. Next we'll take up second. Faraday's second. I've written just first law there. Here, second. Second law is something similar to that first law, but slightly different. What is this blue color solution?
Copper sulfate.
Copper sulfate.
And I can't use appropriate colors, and there is nothing like colorless here. So anyhow, I'll draw this only. This is not copper sulfate. Copper sulfate solution. Silver nitrate solution. It's colorless. Okay. So what I'm going to do? Dip electrodes first. Okay. What is one thing that is different? In second law, I'm going to pass electric current through different electrolyte solution. But what is that important thing to note? I'm going to pass same quantity of electric current. I'm going to pass same quantity of electric current through both the solution. Then the amount of the metal displaced at an electrode will be same or different. Will it be same or different?
Different.
Why it will be different?
Sir, repeat the question.
Equivalent.
Repeat the question. I'm going to pass same quantity of electric current, say 10 coulomb, 100 coulomb, 1 coulomb, whatever coulomb. So same quantity of electric current is being passed through copper sulfate as well the silver nitrate solution. Now in both the solution, the amount of the metal displaced is same or different?
Different.
Different, sir.
Different. And why?
Equivalent mass will be different.
Equivalent mass is different. In which case the metal displaced is more?
Copper.
Silver.
Silver.
Since it is costly now in the market, you can't answer copper. Whatever is the fact you have to. So if I take gold, you will never answer then. Which is correct then? Why copper, Niti Gandhi? Niti Gandhi is absent.
I am here, sir.
Here only. Then tell me. Okay. Prahlad told me, I think, silver. Why silver, man?
I didn't say, sir. I think someone else.
Your voice is having some kind of.
I didn't tell silver that time, sir. It was someone else.
Okay. Who is that silver man?
Me, sir.
Oh, silver man is Sumed. Who is
Yes.
bronze man?
Yes, sir.
Huh. Okay, tell me. Why silver, Sumed?
Equivalent weight of silver is more than that of copper.
That's all the answer. That's all the second law also. Now, whenever equivalent mass is more, metal displaced is more. Combining this entire scenario and all those things, can you people make some statement and take a good prize away? Anybody? What is the statement for second law?
When same amount of charge is passed through two different electrolytes, the mass deposited is directly proportional to equivalent weight.
That's a correct statement. So you can walk away with one problem on this, which I'm going to give you later. Okay, Sumit, this statement. During electrolysis, when the same quantity of electric current is passed through different electrolyte solutions, the amount of the metal displaced or amount of the substance in general displaced at an electrode is directly proportional to its equivalent mass. During electrolysis, when the same quantity of electric current is passed through different electrolyte solutions, the amount of the substance displaced at an electrode is directly proportional to its equivalent mass. That's it. Okay. So mathematically, the mass of the metal displaced is directly proportional to equivalent mass. Now let us make one generalized statement for second law so that we can use it for all numericals to solve the numericals. Okay. Those who are writing can write. Should I give time or written already? I'll proceed. So let us give a standard mathematical form for second law. Let's say we are going to pass electric current through two electrolyte solutions of some substance A and B. Okay, so WA is the mass of metal A of equivalent mass EA. For this, what we can say, WA proportional to EA. When the same quantity of electric current is passed through some solution of electrolyte B, then WB is mass of metal B of equivalent mass EB. Then mass of the metal B displaced at an electrode is directly proportional to equivalent mass of B. Therefore, when we divide that, WA by WB becomes equal to A by E. So WA by WB is equal to EA by E. So by using this equation, you can calculate any one unknown quantity from three known quantities. So they'll generally, the moment they say when electric current is passed through some two different electrodes, HCl and copper sulfate, silver nitrate and zinc sulfate, something like that. So you should think it is about second law, Faraday's second law to be applied. Okay, fine. So if it is done, we shall solve some numericals on this. Shall I proceed now?
Yes, sir.
Okay. We'll take numericals. This page is forwarded. We'll take up next page. Oh. Write down this. Calculate the mass of aluminum deposited at cathode when deposited at cathode when 193 coulomb of charge is passed through molten cryolite containing dissolved alumina. Alumina means Al2O3. This is metallurgy of aluminum. Correct? Alumina is bad conductor. They dissolve that one into molten cryolite, Na3Al6, and then convert Al2O3 to a conductor. Then get aluminum deposited cathode by passing electric current. Come on. And now data, atomic mass of aluminum 27, Faraday constant, you know. Let me see how many of you can give correct answer.
Sir,
Hmm.
0.018 gram.
0.018.
Yes, sir.
Right. Okay. Directly you can use formula or simple arithmetic calculation. So we have this first law, W is equal to E by 96,500 into cube, because quantity is given. Now aluminum, they'll give within the bracket atomic mass or equivalent mass. Since we know, I have not given this. Equivalent mass of aluminum 9 gram into 193. That's all. Okay. If it is done, I'll proceed.
Sir, then what is that cryolite and all?
That is simply story building up. Actually, I told you, no, this is the problem pertaining to extraction of aluminum by electrometallurgy. Metallurgy is done in your college?
It was deleted, no, sir.
Yes.
Oh, correct. But we'll do. We'll do definitely. Not one. Aluminum extraction you have studied in your school probably, right? Iron and aluminum, you didn't study? Oh, everybody is absent. In your school, some metallurgical operations were there, no? Extractions. Yes, from bauxite, that's what they think. Correct, no? You have studied, right? The same thing. Al2O3 cannot be subjected for electrolysis because it is not an ionic compound. It doesn't ionize. So they take Na3Al6, that is cryolite, in molten state. Dissolve alumina Al2O3 into molten cryolite. Then Al2O3 becomes Al-F3. Al-F3 is ionic. It ionizes to give Al3 plus and F minus. Then upon passing electric current, aluminum deposits. That's the meaning. So whatever the story in between or the procedure, for whatever data is there, what is to be calculated, if you focus that much, other distractions should not bother. Okay. So you need the quantity they have given. They want aluminum deposit. That's all. So atomic mass, they will give generally for simple elements like aluminum, copper, and silver. You should know they are quite commonly given elements. That's all. Okay. Shall I proceed, Kishan Balaji?
Yes, sir.
Okay. We'll take a test. second. How many hours does it take to reduce 3 mole of Fe3 plus to Fe2 plus with 2 ampere current? How many hours does it take to reduce 3 mole of ferric ion to ferrous ion with 2 ampere current? Anybody has got the answer? No idea? Okay, find first quantity of current required for 3 mole of ferric to ferrous. Then Q is equal to IT, that's all. Right. We'll take the solution. 3 mole of ferric ion becomes 3 moles of ferrous ion. So for each mole of ferric to ferrous, how many moles
40 hours, 20 minutes.
Pardon me?
40 hours, 20 minutes.
40 or 20 minutes. Right. That's the correct answer. Okay. So for each ferric to ferrous, it requires addition of 1 mole of electron. So for 3 mole, 3 electrons. So charge on 1 mole of electron is 1 Faraday. So therefore, how much is required? 3 Faraday. Correct? No? So for 3 moles, Fe3 plus 2, Fe2 plus the quantity of current required. Q is equal to 3 Faraday. 3 into 96,487. Cool. Therefore, they are asking us to calculate time. They have passed 2 ampere current. I is given. Right? Therefore, Q is equal to IT. T is equal to Q by I. Q 3 into 96,487 divided by 2. So whatever you get into 60 divided by, right now, you have to divide by 60. Convert that one into hours. You can directly do this here. Divided by 60 minutes, divided by 60 hours. How much is that? How much is this?
40.2 hours, sir.
Next. Okay. If it is complete, I'll proceed.
Yes, sir.
Okay. Third problem. Calculate strength of current required to liberate hydrogen gas from acidified water at the rate of 1.12 cm cube per second at ST. Calculate the strength of current required I to liberate hydrogen gas from acidified water at the rate of 1.12 cm cube per second. Again, you need to just find out quantity required to liberate 1.12 cm cube. At the rate of 1.12 cm cube per second means time is 1 second. Q you have to find. I we need to calculate. That's all. Same problem. Same concept, new problem. That's all. Let me know anybody has got the answer. Got the answer? Sumit says 9.65 ampere. Anybody else? Okay. See, 1 Faraday, that is 96,487 coulomb. Liberates 11,200 cm cube. H2 corresponds to 1 equivalent mass. One gram, right? So therefore 1.12 cm cube is liberated by passing So how much quantity is required for 1.12 cm cube is the question. 11200 requires 96,487 into 1.12 means it is 10,000, right? So nothing but 9.6487 cool. Okay, now time is 1 second. I is equal to Q by T. 9.6487 divided by 1 second. 9.6487 ampere. Time is equal to 1 second. I is question. That's all the current strength calculation. Okay. Let me know if it's complete. Is that complete now?
Yes, sir.
Okay. So those who have completed can leave. Time up. We'll meet for the next class. Thank you. Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
So close ಮಾಡ್ತಾ ಇದ್ದೀರಾ ಸರ್?
ಮಾಡಿ.
Okay.
Thank you, sir.
Thank you.